Hello. Welcome to Convergence. My name's Michael Doran. I'm a California attorney. I'm very interested in how technologies are advancing and then coming together, converging to create new concepts and ideas. We live in an amazing time. So, Albert Einstein said, among the most difficult problems in all of physics is Earth's magnetic field. I believe it's among the most difficult problems in all of biology. Today, I want to talk about El Nino, and I believe that what I'm about to say is completely novel, and that our understanding, the state of the science that is, of El Nino is horrific. It comes from the Spanish word Christ child, or the warm one, I believe it's interpreted. And an El Nino event is an event where in the eastern equatorial Pacific, there's a abnormally or anomalously warm oceans. And there's been some sophisticated reading of winds. Sometimes it's called ENSO, or El Nino Southern Oscillation, and that has to do with the pressure index between Tahiti and Darwin. And that's about as sophisticated as it gets. There's weather events that have been correlated with it, of course. But let me just give you a basic question. Why do few people care about the so-called El Nino other than during specific times of the year? Like winter, there's some effects, of course, on the hurricane season, which would be the most intense part of it is typically in the later part of the fall. But there's times of the year where El Nino is just not that interesting. Why? Well, let's talk about mechanism and what precisely, because it's just not, it's been so politicized when you start to talk about carbon dioxide that, and the greenhouse gas theory, and then the so-called skeptics, and everybody's in their lane, and 10 years are at stake, and nobody wants to talk about how different fields are coming together and saying some things. So, and last episode I left off, kind of was cut off. There's a half-hour limit in these shoots. I was talking about cosmic rays. It's a dampened system. These are inputs. But cosmic rays are associated with glaciations, and that has to do, apparently, that cosmic rays, when they're very intense, cause glaciations. And I don't have a paper to cite for you, unfortunately, but the idea is that in the plane of the Milky Way, the solar system goes up and down every 30-some million years, and when we're in the plane, the cosmic rays are at the highest. And so right now we're actually in a glacial epoch, probably having to do with the fact that we're close to the plane of the Milky Way, and we have elevated cosmic ray levels. But we're in an interglacial inside that glacial period. So about 20,000 years ago, we came out of this glacial period, and again, believe it or not, I'm about to talk about El Nino. And there was a study out of it was published in Nature in 1999. And again, I want to be careful to cite different authorities. And I've actually talked about this particular study already in an earlier episode, so I want to properly cite it. It was published in Science magazine volume 283, number 5401, a 15,000-year record of El Nino-driven alluviation in southwestern Ecuador. That was the Ecuadorian lake I was talking about. And I incorrectly said that we've had modern El Niños for the last 4,000 years. It's actually the last 5,000. So let me just be specific, read the abstract. Debris flows have deposited inorganic laminae in Alpine Lake, which is 75 kilometers east of Pacific Ocean in Ecuador. These storm-induced events were dated by radiocarbon, and the age of the laminae that are less than 200 years old matches the historic record of El Nino events. Now, this is me talking. What they're doing is that it's kind of like a control. We say, we look at the record of El Nino that we have in our meteorological record, and then we're looking at the lake bed, and we see that these flows match. So then we can infer that the El Nino condition in the ocean matches what's going on in the lake bed going back in time. And they took a core, and I'm reading now from the abstract, from about 15,000 years to 7,000 calendar years before the present. The periodicity of the clastic depositation is greater than or equal to 15 years. I think I reported to you 17 years. Thereafter, there is a and the reporting that I might have heard might have been that it averaged 17 years, as opposed to the periodicity was greater than 15 or equal to 15 years. Thereafter, there was a progressive increase in the frequency of the periodicities of 2 to 8.5 years. This is the modern El Nino periodicity, which was established about 5,000 calendar years before the present. So I want to say that I believe that this is true, that although I don't, with all the dams that are being built around the world, I'm not sure that if you were to start looking at lake beds around there and how they're behaving now, you're not going to get the same measured quote unquote modern frequency of El Nino. I'm not sure that even exists anymore. But I want to talk about mechanism now, and then hopefully tie it all together. Again, as I've explained, the colder the oceans, the more carbonation they hold. When surface lows go by this water, they are able to remove more carbonation and have more organization and more stacking, particularly tropical storms, and then more cirrus coverage. And cirrus clouds have serious infrared heat trapping ability around 200 watts per meter squared. And to give it a reference point, carbon dioxide is about 4 watts per meter squared. So these clouds are incredibly strong at heat trapping. So in the context of large-scale electrical fields and resonances, longer wave resonances, the freeze rate, the rate at which water droplets, which are carbonated and additionally carbonated by the air from the CO2 that comes out of solution with surface lows, you get an electrical organization of storms that adds to the organization of the storm and then helps these cirrus clouds form and heat trap. And if you recall from an earlier show, I was talking about maybe a simple model of an El Nino where it's like a sine curve. And so it looks just like that, where this is where the water is the warmest and this is where it's the coldest. But then if you take the second derivative of that and you're looking for the rate of change, the peak rate of change of a sine curve is minus sine. So if you model an El Nino, instead of just saying 2 to 5 years as its periodicity, you just make a sine curve and, say it's about like that. It's not a sine curve, but I'm just simplifying it. Then the second derivative of that is a minus sign. And so what you're saying is, in a simple model, is that when El Nino is at its warmest, it's cooling down at its fastest rate of change. When it's a La Nina, it's warming up at its fastest rate of change. And again, I'm talking about, and this is the Lenzine paper really, is I'm talking about the fact that carbonated water, the colder it is, the more carbonation it can hold. Pardon me. And the more of this cirrus production and organization that occurs and traps heat. And but there's another part to this too. There's not just the carbonation in the clouds, but also the electrical complexity. And this is where Lenzine, Hartmann-Fu, other people who studied this, when they picked out grid squares, they're not looking or not capable of looking at this third dimension, really, this complexity of electrical fields and currents that actually alter the clouds. So if you change the electrical currents and fields, then the impact of ocean temperatures is going to change as well. And in this particular case, where it leaks out of the zone, where currents move outside the zone that's being studied, or through the zone that's being studied, that's not picked up what the consequences of the electrical differences are, you're not going to pick that up in your study. And this really turns out to be incredibly significant. And it also, it's internally insignificant within the sea surface temperatures, because the warmer the sea surface temperatures are, the more conductive they become by 1 degree, percent conductive for each degree of warmer oceans, the more conductive the oceans become. So you have a couple of things going on. The carbonation does better levels of carbonation the warmer or colder the oceans are, but the more conductive the oceans become. And sometimes that means that currents escape an area where clouds are not forming, or not forming as well because they're not as carbonated. The currents then escape that area because the oceans are so cold, or so warm, pardon me. All right, so you can actually see this with your own eyes, the electrical complexity. And again, it's another convergence, an area where, and we'll get to spatial computing, but I just want to talk about the worldwide lightning network. So what that website is a collection of people who have monitoring stations, and then the monitoring stations are the data from the monitoring stations go to Washington University, I'm sorry, and the URL is, and this is something that I highly encourage you, if you are interested in this, to look at the website yourself. It's, want to be precise? It's www.lin.net. The page comes up, it looks like that. And I want to talk specifically for El Nino about the 24-hour average. Like today, today's July 2nd, there's 713,677 total flashes per degree square per this website. Again, www.ln.net. And I don't know to what degree this can be picked up by the camera, but it's showing global lightning for the last 24 hours. And I've been monitoring this for a long time. Well, most lightning occurs in the tropics, but 90% occurs over land. And why is that significant? Well, there is a difference between the northern and the southern hemisphere. There's more land in the northern hemisphere. I'll argue that the MSU data, for instance, there's more warming occurring in the northern hemisphere, with the exception of around the peninsula of Antarctica and the tail of South America, because since there's more lightning that occurs in the northern hemisphere because there's more land, it's like you can't tell that you have a 200-watt light bulb in the socket as opposed to a 100-watt light bulb until you flip the switch, until you have the currents. And we're seeing what added carbon dioxide is doing to the northern hemisphere. It's Antarctica is melting much more rapidly during a very specific period of time when there's high levels of lightning. So now back to El Nino. So what's been observed is a dramatic seasonal difference between what occurs during the winter months and what occurs during the summer months, because, again, for the same reason that lightning has a land orientation to it. So, for instance, there's a period of time like right now where and I don't know if this will pick it up, but you can see Africa. The fat part of Africa is getting a lot of lightning. Again, I don't know if you're able to pick that up from my cell phone, but and this corresponds to the tropical storm season. As global lightning gets down into the winter time for the northern hemisphere, the sun's going or the Earth's going around the sun, and that tilt decides the conditions for lightning. In the southern hemisphere, there's less land, so there ends up being less global lightning, and that's why, even though the orbit of the Earth around the sun is elliptical, and during January we're actually closest to the sun, that's the slowest time of the year for tropical storms, because the southern oceans haven't warmed up yet, and global lightning isn't very high, because there isn't as much land for lightning to be produced, and so these tropical storms are driven by the electrical currents created by lightning, and so there's less lightning and there's less tropical storm, and there's less conductive places for capacitive couplings to help organize the storm. But interestingly enough, the Southern Ocean starts to play a role. And what I mean by that is, so you have North and South America. This is going to be like a stick figure. You have Africa, and you have Europe, and then you have Asia, and then you have Australia, and so forth. Again, this is just a very crude drawing of what the land looks like, and it's if I had a globe I could show you, but it's not going to help make my point. But so you have the Americas, you have Europe and Africa, and then you have Australia and Asia, and then you have this vast area that's open. That's the Pacific Ocean. And if you were to organize charges, and this is what shows up on this website when you look at the 24-hour average during the time of El Nino, what you see is the southern oceans, which are continuous in a circle, are always going to be a common for electrical flows and currents, and charge organizations. And so what you end up happening is lightning going over the land masses in equal area. So you get 3 areas of lightning, one over the Americas, one over Africa, even though you're on the thin part of Africa. And then you're in Australia, you have 3 areas of lightning, but then you have this 4th quadrant in the Pacific Ocean where there's no land. But it ends up that the charges, like positive and negatives, it's just like air pressure too in terms of organization, where like charges repel each other and opposite charges attract, and high air pressure is attracted to low air pressure, but it takes energy to create more lower pressure or higher pressure. It's the same thing with charge accumulations. And when you have these charge accumulations, you change the potential differences and you make it more likely for lightning to occur in thunderstorms. And so even though it's rare to have thunderstorms and lightning over the oceans compared to land, it starts to really occur in the wintertime when there's El Nino over the Pacific Ocean in a very organized way, because you have a common area where currents can flow, unlike the northern hemisphere. So even though there's more lightning there, you end up getting more of a horizontal organization of charges rather than these 4 quadrants. And one of the quadrants basically is what's interacting with the area of El Nino. So it ends up being expressed from a weather standpoint for everybody to see at that time of the year, not really as much during the other times of the year. Now, getting back to this study that was published in Science. So what occurred is we came, well, during the glacial, you had this Banjonian, I'm probably destroying that, but in South America, you had along the Andes and so forth this ice cap that ran all the way to the peninsula of Antarctica, and the oceans were lower, and there was basically solid ice, not ocean, between South America and Antarctica. So you didn't have a continuous area where electrical currents could flow through the salt water. It was broken up. And it took some time for some of these things to melt away, for the antenna features of the continents to be exposed and ice-free. And so that seasonally you could start to get these signals that El Nino would pick up. And that's why the frequency, in my opinion, changed. And the modern period of time, then you have the frequency of between 2 and 5 years. Now, of concern, most of these interglacials last about 10,000 years, and we're right at 10,000 years. So what happens? I mean, there's people that have speculated why the interglacial ends. One thought is, again, this is a phenomenon that involves not just the lightning and the global currents don't just involve the air; they also involve the subterranean. And again, how do you heat up your toast? You push the lever down and to heat up your bread and make toast. And what happens to the wires? Well, the wires glow red, and they heat up your toast. Well, how does that happen? And there's an electric current that flows through the wires and heats it up. And when you have these currents, and in this case, currents that are going through a specific part in the middle of Pacific Ocean, because you have these 4 quadrants, 3 already exist, and then you have this organization. Again, you can go to the website and see it with your own eyes during the winter. It's there all along. right in the middle of the Pacific Ocean. It just happens to match the hot spot in the ocean that helped form the Hawaiian Islands. Well, how did it get hot? I mean, that's a question that no one asks. Well, how did it get hot? It's hot there, but it's not hot over here. Well, how did that happen? The heat just magically appear? So I think that hot spot is a result of electrical currents from lightning, ultimately. Plate tectonics, the whole Pacific Ring of Fire is all part of this living Earth that has come over incredible timescales. But it's a dampened system. It's it's highly tuned, and we can expect the glaciation to end. I mean, the interglacial to end with a glaciation. Okay, I've said a mouthful for today, and I'm kind of tired. I'm stumbling over my words more than usual. Please click the like button, subscribe. It's going to take some time for this to catch momentum, but I believe it will. Carbon dioxide is not interesting as a greenhouse gas. It's also dampened for that reason. It's dampened. It has to be. It can't be chaotic. The Earth is alive, and El Nino is one of the biggest dampening I'm tired. It's the biggest climate feature we have, or weather feature we have, as far as cycles, and it's a huge dampening cycle. But it's getting weird. It's not doing what it's normally has done in the past, and we've had a tremendous amount of climate stability the last 5,000 years. Our population has gone to 7 billion plus. And it's because climate's been stable, and we don't want to go back to the ice age. We don't want to go back to instability, but we're doing things to the living Earth and to the feedback systems that provide the stability that we have. All right, have yourself a good luck, and see you in the next episode.